for my next trick, I'm going to solve some more stuff. X, Y, 150, 150. Okay, and the radius of the hole cut in my rectangle here is 75 millimeters. And I want to find the composite body centroidal moment of inertia about the x prime axis, the y prime axis, the centroidal polar, and all of their stiffness ratios. Okay, now I'm going to do this by solving directly to the centroid, and I'm going to use parallel axis theorem and composite bodies. Okay, so our solution is going to be the composite body centroidal moment of inertia is equal to the sum of each individual centroidal moment of inertia, their areas, and then the distance I want to travel squared. Okay, so first thing I'm going to do is find the centroid, and for this rectangular shape it is symmetric about the horizontal axis, so that would be my x prime axis, and then it is slightly over here for the y, and this is at 219.79 for the composite body centroid. Now my composite body is made up of a rectangle that is solid. So this is going to be my area number 1, and a circle that is removed. Oops. That would be area number 2 of my composite bodies. All right. Now the easy one here is going to be x prime, because it is already, everybody already has a centroid in the x prime. The centroid for the rectangle lies on the x prime, centroid 1, and the centroid for the circle lies on the x prime, centroid 2, okay? Because it's symmetric about the x prime axis. So sticking with my colors here, I x prime bar. This is similar to the last example where everybody was on the x-axis. Well, this one, everybody's on the x prime axis, right? So I x prime, which would be my horizontal, is equal to, okay, red is going to be my rectangle. So moment of inertia for a rectangle about its centroid is base 420 times height 300 cubed divided by 12 over 12 for the centroid. And then I'm going to subtract my circle minus circle, which is pi over 4 times the radius, 75 to the 4th. Okay, and this is equal to 920 times 10 to the 6th, millimeters to the 4th. I x prime bar. That's the composite centroidal moment of inertia about for this entire shape. Okay, I'm saying redundant things, but I wanted to hit home. All right, So that is each individual centroidal inertia added together. Now Iy prime bar, not as nice, because if we look at these distances, okay, the circle is 150. The rectangle is 210 from the y-axis. 210 from the y-axis. And the composite body centroid is 219 from the y-axis. Okay, so they do not all have the same distance like X did. Everybody was 150 from the x-axis, but Y, they're all different. Okay, so we're going to have to do parallel axis theorem for this one. So again, sticking with my colors, Iy is equal to, okay, we can only move the centroid. So the centroidal moment of inertia for my rectangle is going to be height 300 times base 420 cubed divided by 12. And then I need to move it 420 times 300. So there's my area times the distance I want to travel. So 219.79 minus 210 quantity squared. Okay, and that gives me this tiny little distance here, dx1. All right, that's the distance I want to travel. And then I'm going to subtract my circle. Circle has a centroidal moment of inertia of pi over 4 times 75 to the 4th. Inertia doesn't change on axis for circle because it's a circle. Plus the area of a circle, which is pi r squared. And then the distance I want to travel, which will be 219.79 minus 150 quantity squared, end bracket. And that is going to be this distance here, dx2. Okay, I want to travel from the circle centroid to the composite centroid, and the rectangle centroid to the composite centroid. Those are all of my distance x's in this case because I'm doing inertia about the y. So my composite centroidal moment of inertia about the y prime axis is equal to 1.75 times 10 to the 9th millimeters to the 4th. So my polar moment of inertia about the centroid, Ix prime bar plus Iy prime bar, and that will be 2.67 times 10 to the 9th millimeters to the 4th. And now that I have all those, I can get my radius of gyration. Ooh, I need my area. Area is equal to the rectangle, 420 times 300 minus pi times r squared. And this is equal to 108.3 times 10 to the 3rd power millimeters squared. So radius of gyration for the composite body about its centroidal x prime axis is equal to 920 times 10 to the 6th millimeters to the 4th divided by 108.3 times 10 cubed millimeters squared, square root. That is equal to 92.2 millimeters. Doing it for y. Radius of gyration about the centroidal composite body y prime axis is equal to 1.75 times 10 to the 9th millimeters to the 4th divided by 108.3 times 10 cubed millimeters squared. And this is equal to 127 millimeters. And then the radius of gyration for the polar moment of inertia about its centroidal radial axis is equal to 2.67 times 10 to the 9th millimeters to the 4th divided by area, 10 cubed millimeters squared, and this is equal to 157 millimeters.